Sturm-Liouville theory. What's that? Well, with Sturm-Liouville theory, we come back to the idea of separation. Let me just recall a few things which we did already. Right? In separation, the key idea is to write the solution of a PDE as functions which only depend on one variable. So in this case, x of x, t of t. Right? And then we subbed it into the differential equation, and we use the fact that, for example, a spatial x derivative would only act on the capital X function, but not on the t. A partial time derivative only acts on the time, but not on the space. Okay? And then sometimes we have a second order derivative, so we do that once again. And doing this, then we could separate all the t functions putting on the one side and all the x functions on the other, and see that it has to equal a constant. So then often we get a time problem. For example, t prime plus lambda t is equal to 0. And then we got a spatial problem. For example, x double prime plus lambda x is equal 0. So this would happen for the homogeneous heat equation, for example. With boundary conditions, x at 0 is 0 and x at L is 0. So then this is homogeneous Dirichlet boundary conditions. And this spatial problem, this is a Sturm-Liouville problem. That's the key idea. Okay? And what do we know of this already? We know we can solve this, right? We did the cases lambda less than 0, lambda equals 0, lambda positive. And we only find something for lambda positive for very specific values of lambda. Lambda n is n square pi square divided by L square. And this is what we call the eigenvalues. And here n is larger or equal 1. And we also found the corresponding eigenfunctions. Do you remember the eigenfunctions? We called them, I think, phi n of x, and these were just the sine functions. Sine n pi x divided by L. So for each eigenvalue, we have a corresponding eigenfunction. And this is why we often call a problem of this one here in the box also a Sturm-Liouville eigenvalue problem. So then the idea is to find the solutions and the eigenvalues. So a Sturm-Liouville eigenvalue problem. So then this entire chapter 4 is about generalizing this idea. So here I show you one example, but of course there are many, many more examples. And that gets really interesting theory. The good thing is that we get strong, powerful results which allow us to work and to calculate these functions. A regular Sturm-Liouville problem denotes a problem of the form here in the box. So p of x phi prime prime plus q of x plus lambda sigma of x phi is 0 on an interval from a to b. And then we have general boundary conditions of the form alpha 1 phi at a plus beta 1 phi prime at a is 0. Alpha 2 at phi of b plus beta 2 phi prime at b is also 0. So this could be the boundary conditions. They could be of homogeneous Dirichlet type or of Neumann type, or they are homogeneous Robin boundary conditions or boundary conditions of the third kind. Now here in conditions 1, 2, 3, you have a few conditions. So the p prime, q, sigma are real valued and continuous. P is positive, sigma is positive. These are important. And then the alpha beta values are so that they are not 0 at the same time. So if alpha 1 is 0, then beta 1 is not. Or if alpha 2 is 0, beta 2 is not. And so that's a fancy way to write down that there shouldn't be 0 all at the same time. Let's compare our little example which I just had before. If I have x double prime plus lambda x is 0, x at 0 is 0, x at L is 0. So how does it match? So comparing the first term, here we have p of x phi prime and then in brackets prime. So if we choose p is 1, then this is great. So p of x is equal to 1. Then we have the first term. And then the q term times, we have no q, so then the q term is equal to 0 here. That's fine as well. And the sigma term is equal to 1. Then here we get a lambda phi, which is in lambda x in the x notation. The interval is from 0 to L. So then we have that. And for the alphas, we only have Dirichlet conditions. So we have this and this. So then we have alpha 1 is 1, alpha 2 is 1, beta 1 is 0, beta 2 is 0. All right, so the red equation here is a regular Sturm-Liouville problem, and we can assign all the values, and you can check they satisfy all the conditions 1, 2, and 3. So writing it this way is a quite cumbersome way to write down the simple Sturm-Liouville problem, but of course this will be useful if we treat more complicated, more complex Sturm-Liouville problems. So here are a few notions which we need to be aware of. There's always the trivial solution. You can always set phi as 0. In other words, this problem is a homogeneous problem. So it always has a trivial solution, which of course we are not interested in. We are interested in non-trivial solutions, which are non-zero. Lambda is called the eigenvalue, as we did before. The solution phi, which belongs to the lambda, is called the eigenfunction. And together, we call them the eigenpair. Makes a lot of sense, right? Okay. Then all the eigenvalues together are called the spectrum. The spectrum is a set of all the eigenvalues. Now a Sturm-Liouville problem is called singular if any of the conditions 1, 2, and 3 are not satisfied. And this will actually happen in some of the examples we study. So that's why I mention it here. Now, let's do an example which is maybe not as easy or as trivial as the one before. So we have phi double prime plus 1 plus lambda x divided by x phi is 0. Phi at 1 is 0, phi at 2 is 0. So you should already be aware that you are dividing by x, okay? So x should not be 0, otherwise you are in trouble. The boundary conditions are given at 1 and 2. So we have 1 is less or equal x, less or equal 2. So we are lucky, because x is 0 is not part of this interval, so we have no trouble with the denominator. Now let's see if this is Sturm-Liouville problem. So let's put it in Sturm-Liouville form by just multiplying out the bracket. So this is 1 over x phi plus lambda phi is equal to 0. Now I like to compare this to the general Sturm-Liouville problem from above. So let me write down the general form of the Sturm-Liouville problem here below. It was p phi prime prime plus q plus lambda sigma phi is 0. Just the equation. Okay, then we can compare. So here we need to choose the p function is equal to 1. The q function is the 1 over x for this term there. The sigma function is also 1, so this is all great. And then for the boundary conditions, we have again Dirichlet conditions. So alpha 1 is 1, alpha 2 is 1, beta 1 is 0, beta 2 is 0. Check. Okay, so this thing here, example 4.1, is a regular Sturm-Liouville problem, because division by 0 will not happen since we are in the interval from 1 to 2.